Okay, so welcome you to today's lecture. Do you have any doubts from your earlier lectures? So what, no questions? So what we did so far in testing of hypotheses is that we derived, first we studied the Neyman-Pearson lemma, which helps us in finding the most powerful tests for testing simple versus simple. Then we came to one-sided hypotheses, which are composite hypotheses. And we saw that if your distributions are such that they have MLR, then it is possible to get uniformly most powerful tests, even for one-sided hypotheses of the kind H naught theta less than or equal to theta naught against theta greater than theta naught, or vice versa. Then last time we were discussing about the two-sided hypothesis. What happens if your null hypothesis is two-sided? That means your acceptance or rejection region could be on both the ends, larger and smaller values. Right? For theta less than or equal to theta naught, it is only for smaller values you're favoring H naught. For larger values, you're favoring theta naught. But there may be situations where you may be favoring H naught for large as well as small values of theta. So something like H naught theta less than or equal to theta 1 or theta greater than or equal to theta 2. And we are interested in finding uniformly most powerful test under such situations. But before I do that, let us recall the Neyman-Pearson lemma. We did a Neyman-Pearson lemma. Neyman-Pearson lemma gives you a test, the best test among all tests which satisfy beta phi theta naught is equal to alpha. Right? If you have to test theta 1 is equal to. And then you maximize the power beta phi of theta for any theta is equal to theta 1. Right? That is what. Now let us try to generalize this. I want my test satisfies two conditions at 2 points, theta 1 and theta 2. Beta phi theta 1 should be gamma 1. Beta phi theta 1 is also alpha, and beta phi theta 2 is also alpha. And I'm looking at all the tests which maximize beta phi theta 3. Theta 3 is some other point. We saw that Neyman-Pearson lemma can be extended even to this situation. The only difference now is there it was theta, if theta 1 was there, so g theta 1 bigger than c times g theta naught. Now it would be because you are trying to maximize g theta 3. So theta 3, so g theta 3 is bigger than c1 times g theta 1x plus c2 times j theta 2x. That is the generalized Neyman-Pearson. I did that, right? I guess. Yeah. And then we saw that this test also maximizes this E theta 3 phi among all tests which satisfy E phi theta 1 is less than or equal to alpha and E phi theta 2 less than or equal to alpha, provided these CIs are non-negative. Okay. Now it is this generalized Neyman-Pearson lemma which would be useful in the two-sided hypothesis. If simple versus simple, it was only this thing. So we'll see how it is. So what I would require is I would require that my phi satisfies beta phi theta 1 is equal to alpha, beta phi theta 2 is equal to alpha, and then I try to maximize beta phi theta 3 among all tests which satisfy this. And the solution is provided by the generalized Neyman-Pearson lemma, which I have stated. And what does the solution says? Yes, phi should be 1 if, yeah, you're trying to maximize theta 1. So density at theta 1 should be bigger than linear combination of densities at theta 1 and theta 2, right? So g theta 1 x should be greater than c times, sorry, theta 3 is the point where I'm trying to maximize. So g theta 3x should be bigger than c1 times g theta 1x plus g c2 times. You see, I'm trying to say that because that would come into the proof. It should not look like a very strange thing to you. That is why I want to keep it in your mind that it is the generalized Neyman-Pearson lemma, which is very much similar to the usual Neyman-Pearson lemma. There, I was interested in maximizing beta phi theta 1 subject to beta phi theta naught is equal to alpha. Now I have two conditions. My beta phi theta 1 should be alpha. beta phi theta 2 should be alpha, and I have to maximize beta phi theta 3. Theta 3 is some other point. So now I have 3 points. In earlier situation, I had 2 points, theta 1 and theta naught. I wanted beta phi theta naught is equal to alpha and wanted to maximize beta phi theta 1. And the solution is whatever you're trying to maximize, look at the density at that point. G theta 1x is bigger than constant time wherever that condition is given, b beta phi theta naught is equal to alpha. In this case, I have 3 constants. There I had 2 constants. Here I have 3 constants: theta naught, theta 1, theta 2, and theta 3, let us say. And I want beta phi theta 1 is alpha, beta phi theta 2 is also alpha, but I have to maximize beta phi theta 3. Generalized Pearson lemma says the solution is provided by G theta 3 density is bigger than linear combination of densities at theta 1 and theta 2. So just keep that in mind. Then the whole proof would be straightforward to you. It should not come as a surprise to you. Okay, so now let us move to this. Yeah, any questions in whatever I said right now? Okay. So UMP test for two-sided hypothesis. So let us consider the following hypothesis: H naught that theta is less than or equal to theta 1, or theta is greater than or equal to theta 2. So here H naught is favored for small values and large values. That is why it is a one-sided hypothesis. Versus H1 that theta lies between theta 1. Another kind of hypothesis could be H naught that theta lies between theta 1 to theta 2. Versus H1 that theta is less than theta 1 or theta is greater than theta 2. Third kind of a hypothesis could be H naught that theta is equal to theta naught versus H1 that theta naught equal to theta naught. Right? Where these theta naught, theta 1, theta 2 are specified points in the parameter space. Where theta naught, theta 1, theta 2 belonging to theta are specified. Now, these kind of hypotheses are called two-sided hypothesis. So incidentally, in this situation, in earlier situation where we had one-sided hypothesis, we were able to derive MP alpha tests in all situations where I have a MLR property. Now, in this situation, that will not be the case. If I have to derive a general result, it would be only for exponential family. Other thing, again, I said I have to do it by a basic first principle, that is in the Neyman-Pearson lemma. So like uniform zero theta will not be covered in whatever result I'll be doing, because it will be for only exponential family. So only for exponential family, only for two-sided hypothesis. One-sided hypothesis, I was able to derive it for MLR, where uniform is also covered. But in this case, I'll be able to derive results only for exponential, but that doesn't mean that it doesn't, result may not hold, or most powerful test doesn't exist for other situations. Other also it may exist, but then each case has to be dealt with separately, like uniform theta, theta plus 1, right? You see, uniform theta, theta plus 1 doesn't even have a MLR. So that is altogether a different ball game. So suppose X has PDF belonging to one parameter. Exponential family f theta excuse me, is exponential to power beta theta tx minus beta theta into hx. Right? And eta theta contains the range of eta theta contains an open rectangle or open interval in, so collection of all those eta theta contains an interval. Right? Now, in this case, what happens? What is a complete sufficient statistic? Tx. So it is, in fact, minimal sufficient, right? So Tx is complete sufficient and hence minimal sufficient. In fact, I know what would be the PDF of Tx. Can anyone tell the PDF of T would be? Yes. You see, when you use the Jacobian method, the transformation would correspond to Tx equal to some quantity small t, right? And then a Jacobian term would come, which will normally involve x. So then density would become just exponential eta theta t minus b theta into h star x. H star x would involve Jacobian term and the inverse of these x's with respect to that transformation eta theta is equal to t. Eta x equal to, sorry, tx equal to t. So the PDF would be how much? Anyone? Can anyone tell? Would be, yeah, g theta t would be how much? Yeah. Just in place of tx, you put t, because that is what the transformation you will put, right? Exponential eta theta t minus b theta into some function of t, which you can call as m of t. Is that okay? That would be a density. So again, t is complete sufficient. And I know that if you have a minimal sufficient statistic, it is enough to consider those test functions which depend on t, right? Because otherwise you can, given any other test function phi, you can construct a new test function, expected phi x given t, which depends on t. It does not depend on theta because t is sufficient. And it has the same power function as phi, right? So it suffices to consider test functions depending on tx, right? And you know why? Because for any other test function phi, you can define a new test function expected value of phi given t. Now note that since t is sufficient, expected value of phi given t is just will not depend on theta. And since phi is between 0 to 1, expected value of phi given t would also be between 0 to 1. So it is a proper test function. And what would be its power function? Power function is expected value of phi star t. And what is expected value of phi star t? Because if I consider the power function of phi star, that is expected value of phi star t, that is expected value of phi given t. And what is the expectation of a conditional expectation? Expectation itself. So that is expected value of phi, which is beta phi theta. So given any test function which does not depend on minimal sufficient statistic t, I can construct a new test function which depends on a minimal sufficient statistic and has the same power function as the given test function. So it is enough to consider test functions which depend on observations only through t. And reason for that is because then for me, this considering this density is good enough. All right. Now let me do a lemma, which I'll require, which again, I would say if you use your statistical mind, this lemma would look like a trivial thing. Okay, let me ask you. Suppose this suddenly has if eta theta is increasing, then this has MLR, right? Because for theta 2 greater than theta 1, it has MLR. If it has MLR, what does that mean? Larger values of t should correspond to larger values of theta. So now, suppose you have a function psi, which is up to certain point is less than or equal to 0, and beyond certain point it is greater than 0. Then what can you say about expected value of psi? Because larger values of psi should correspond to larger values of theta. So that suggests that once expected value of psi has achieved a positive value, beyond that theta it should remain positive, right? That is what the intuition says, right? So what I'm saying is psi becomes positive beyond certain point. Psi is that kind of a function. And if then larger values of theta corresponds to larger values of x. And psi, I know beyond certain point is always positive. So same property should be possessed by expected value of psi also, because expected psi and psi say the same kind of a thing. So next lemma basically says exactly that thing. Now you have to write it down mathematically. That's all. How to write down what we have thought about heuristically. Okay? Our heuristic suggests, or in other words, what does it say? If you have suppose you have a MLR, and you have a function psi which changes sign at most once. And if it changes, it is from negative to positive. That means in the beginning it is negative. Either it doesn't change, psi is such a function, either it doesn't change, or if it changes only once from negative to positive. That means if from negative it has moved to positive, then it will remain positive throughout. Then what is the kind of a property you would expect from expected value of psi? Exactly the same you would expect. That either expected psi doesn't change sign. But if it changes sign, it should change from negative to positive only, because psi is changing that from, and you have MLR. That is what exactly, and next result is exactly that. The only thing is I have to write down that mathematically. So I have to use my mathematical maturity to write down something which a layman even can understand, right? So let me write down this lemma. Suppose suppose that a random variable t has a PDF or PMF in the family P of P, let me call as a parametric family, G theta. So let me call this as H theta, right? This need not be exponential, right? Any reason. That's it. Where theta belongs to R. Suppose that this family has MLR in some statistic T. MLR in T. Let psi be a function with single sign change. What does that mean? That is, there exists a x naught such that psi x is less than or equal to 0 for all x less than x naught, and psi x is greater than or equal to 0 for every x greater than x naught. Yes, any question? Single sign change. It changes sign only once. Its sign will be positive or negative. Sign means it is positive or negative. It has a single sign change. That means up to in the beginning it is less than or equal to 0, and then it is positive. So it has a single sign change, and sign change is from negative to positive, right? That is also important. Single sign change Yeah, it has MLR in T. Random, you may have a sample, right? X1, X2, Xn. Where? Suppose that? Yeah, so suppose I have, so what you can do is suppose that a random variable T or a statistic T, so it has a MLR. So basically assumption is T has MLR in this for this family, right? That is what it says. This family, so you have a family of distributions which has MLR in statistic T. So if you want me to correct it, yeah, so your observation is correct. Slightly there is ambiguity in the statement. So the statement can be modified as, suppose that let P be as theta, theta belonging to theta, be a family of PDFs. PDFs or PNFs. Where theta is subset of R. Right? Suppose P has MLR in T. Is that okay now? So let psi be a function with single sign change from negative to positive. Actually, this also covers the case when there is no sign change. Your x naught technically could be infinite also. So that covers this case also. So, but yeah. So then first part says, then there exists a theta naught such that E theta psi t is less than or equal to 0 for every theta less than theta naught, and E theta psi t is greater than 0 unless E theta psi t is either positive throughout or it is negative throughout, right? Is either so what it says is, if you have a family of PDFs which has MLR in T, and if psi is a function which is changing sign once from negative to positive, right? Then if I consider expected value of psi t, there are three possibilities. Either expected value of psi t is always less than 0, or expected value of psi t is positive throughout. But if t takes values from both values negative and positive, then once it becomes positive, it will remain positive throughout, right? That is what it says. So in fact, you can write down this thing. So that covers, unless expected theta is either positive throughout or negative throughout, right? That is what it is. Suppose g theta x is positive for every x and theta, that h theta 2, so this is not g, you can write down h, that h theta 2t upon h theta 1t is increasing in t whenever. So now this has this family, the whatever, yeah, h theta 2t upon h theta is increasing in t whenever. I'll have to correct statement a little bit, but I'll come to that later on. Actually, here now s theta is a PDF of t, not. So this h star theta is a PDF of s theta is basically a PDF of t. So I should, yeah. So actually it should be, let me just correct it right away so that you don't make any mistake. Let f theta, which could be like this, which need not be exponential family. Let f theta be a family of PDFs, PMS where theta is like. Suppose that P has MLR in T, right? Let psi be a function with single change sign from negative to positive. That is what it happens. Then there exists a theta naught belonging to theta such that expected value of psi t is less than 0 for theta. Yeah. Suppose now this g theta is a density of t. Suppose density of t is such that it is positive and g theta 2t upon g theta 1t is increasing in t for every theta 2, and that probability that psi t is not equal to 0 is positive. So that means psi t is not identically 0. Then if expected value of so you can write down is strictly increasing, right? If E theta naught psi t is 0, then E theta 0, E theta psi t would be less than 0 for every theta less than theta naught. And E theta psi t would be greater than 0 for every . So what it means is once you have expected value of psi t as 0 at some point, then below that point, expected value of psi t would be less than 0. Above that, it would be greater than 0, provided this ratio is strictly increasing. So strictly increasing in important, right? So let's try to prove this. And what does the first part says? If you have MLR, and at certain point, if expected value of, then they'll always exist at point theta naught, such that below that point it is less than 0, beyond that point it is greater than 0. Okay, so let us try to see that. So first, suppose that I have a function of psi of this type. Suppose there exists a x naught belonging to R such that psi x is less than or equal to 0 for every x less than x naught, and psi x is greater than or equal to 0 for every x greater than equal to x naught. So what I need to show in the first part? What I need to show in the first part? So first part, what to show the first part, what you need to show? You have to use your mind. Yeah? Why you sit like a dumb? In the first part, what do you need to show? There exists, that is a statement, but I'm trying to simplify that. What suffices to prove? See, one possibility is that expected value of psi is negative throughout. Then that theta naught is equal to infinity would work, right? It says unless that case is not covered because expected, it says unless expected psi t is either positive or negative, even in that situation it may not happen. So that means you are assuming that if psi theta, if expected value of psi takes both positive and negative values, then there will exist a theta naught below which it will be less than 0 and beyond which it will be greater than 0. So to prove this, it is enough to prove that once expected value of psi t becomes positive, it will remain positive throughout beyond that point. That is what it suffices to prove. Is that okay? So let theta 1, theta 2 belonging to theta, and theta 1 is less than theta 2. So what is my claim? My claim is if e theta 1 psi t is positive, then e theta 2 psi t would also be positive, right? You see, I want to involve you in the proof so that you can appreciate the proof. Otherwise, it becomes a very boring, very scary notations and everything. It becomes a very boring exercise. Is that okay? Have I simplified my claim or not? I just require to prove this. Right? If theta 1 and theta 2 are 2 points, if e theta 1 psi t is positive, then e theta 2 psi 2 also has to be positive, provided theta 2 is greater than theta 1. So suppose that e theta 1 psi t is positive and theta 1 is less than theta 2. Now I'll show that e theta 2 psi t is also positive. So let us consider this point x naught where this change is happening. See, finally, basically what I have to write down is e theta 2 psi t. I'll write down as g theta 2 psi t. Right? No, I know the MLRs are somehow g theta 1 and by g theta 2 and those kind of things have to. What is known to me is e theta 1 psi t is positive. So first, now note that if g theta 2 x naught upon g theta 1 x naught is infinite, what does that mean? Then suddenly g theta 1 has to be 0 for all t greater than or equal to x naught because it is increasing. G theta 2 x upon g theta 1 x is increasing. So if it has become infinity, that means that x naught g theta 1 x naught has to be 0. And then it has to be infinity throughout. 0 by 0 case will not be covered. So that would be positive. So that means beyond x naught g theta 1 has to be 0, right? This implies that e theta 1 t is 0 for all t greater than or equal to x naught. You see, I'm trying to show that this situation cannot arise. So what can you say about expected value of psi t? E theta 1 psi t. It would be minus infinity to infinity, t less than x naught and t greater than x naught of psi g theta t. But for t greater than or equal to x naught, g theta 1 t is 0. So it would be only minus infinity to x naught psi t g theta 1 t t. But for t less than or equal to x naught, psi t is less than or equal to 0, right? Because that is what it is going. Psi x is less than or equal to 0. So that means this is less than or equal to 0. But you are given that E theta 1 psi t is positive. So that means I cannot have g theta 2 x naught upon g theta 1 x naught to be infinite. So this g theta 2 x naught upon g theta 1 x naught has to be some constant which is less than infinite. So this implies that g theta 2 x naught upon g theta 1 x naught has to be some constant which is less than infinite. But I know that g theta 2 upon g theta 1 is increasing in t. Which one? This one? Expected value. From this is less than or equal to 0 is okay. So E theta 1 psi t is less than or equal to 0. But what is given to you? E theta 1 psi t is positive. So that means whatever I assume cannot be true. What I had assumed? G theta 2 x naught upon G theta 1 x naught to be infinite. So that means that cannot be true. So that means G theta 2 x, because if that is true, then my E theta 1 psi t is less than or equal to 0, which is not true. So that means A implies B is equivalent to saying that negation of B implies negation of A. Is that okay now? So that means G theta 2 x naught upon G theta 1 x naught cannot be infinite. It has to be some finite quantity. C. That is what I mean. But now I know that G theta 2t upon G theta 1t is increasing in t. You see, I have, let me honestly commit, I have created some mess over here in this statement. And thanks to him for pointing it out. I don't need anything f theta, g theta. I just need a PDF of t. So basically that g theta I need. Because what I've said is, I want to restrict my test functions only on t. So I need the density of t. So what I need is that density has MLR in t. So that means g theta 2t upon g theta 1t is increasing in t, right? So that is what exactly I need, and I don't need anything else. It's all other family of PDFs, you can forget about it. You want me to correct it? I can just do it. It will just. So what I am saying is, so let us consider the same PDFs that P, which is G theta, theta belonging to theta. Let this family have MLR in T, right? So that means G theta 2t upon, and D theta t is my this thing. So for the time, because I'll be dealing only with exponential, so let us talk about all of this, where theta is subset of R. Let psi be a function such that there exists x naught with gx less psi x less than or equal to 0 for every x less than or equal to x naught, and psi x greater than or equal to 0 for every x greater than x naught. That's all. Simple, right? So G theta is that. That is what I need. Okay, now I can come to over here. So what I saw was G theta 2 x naught upon G theta 1 x naught is equal to infinite cannot be true. So that means g theta 2 x naught upon g theta 1 x naught is C. What does that mean? Because g theta 2 upon g theta 1 is increasing in t. So that means g theta 2t upon g theta 1t would be C, would be greater than or equal to C for all t greater than or equal to x naught. This implies that g theta 2t upon g theta 1t would be same as C for all t greater than or equal to x naught. Is that okay? Because g theta 2t upon g theta 1t is increasing in t. Okay, now so let us consider E theta 2 of psi of t. Right? E theta, any doubt here? Let us consider, so I have to show now E theta 2 psi t is positive. So I consider E theta 2 psi t, which is integral over psi t g theta 2t dt. Now note that somehow I have to use the MLR property. So I have to divide it by g theta 1, but I can divide over g theta 1 only where g theta 1 is positive. So I write down this in two parts, where g theta 1 is positive and where g theta 1 is 0. Right? So let me write down this as, and 0 by 0 form should also not be there, right? G theta 2, so that also have to. So I divide it into two parts, A psi t g theta 2t dt plus A complement psi t g theta 2t. Idea is very simple. The only thing is I am writing down correct, mathematically correct statements so that 0 by 0 form doesn't come and infinity doesn't come. And what is my A? I consider A where g theta 1t is 0. But if g theta 1t is 0, I would not like to have g theta 2t 0 because I have to finally get g theta 2t upon g theta 1t. So g theta 2t is positive and A complement is basically collection of all those t such that g theta 1t is positive or g theta 2t is 0, right? G theta 2 are densities, right? What can you say about the points in A? What can you say about the points in A? Points in set A. Note that over here. What is happening to g theta 2t upon g theta 1t in A? Infinity. And what is g theta 2 x naught upon g theta 1 x naught? Some finite quantity. So can you conclude what would happen to points in T? For points in T, what would happen to? They would be bigger than x naught, less than x naught. What would be their position relative to x naught? Because you see, at point x naught, g theta 2 x naught upon g theta 1 x naught is a finite quantity, and it is increasing. And I know that on set A, it is taking infinite values. So that means all the points in A should be bigger than or equal to x naught. Then only it can happen, right? Right? So this has to be contained in x0 to infinity. If it is contained in x0 to infinity, what does that mean? G of t, sorry, psi of t over here should be greater than or equal to 0, right? Okay. So here, if psi t is greater than or equal to 0, so I can write down this simply as greater than or equal to a complement psi t g theta 2t. So a complement is over a set g theta 1t or g theta 2t is 0. But at g theta 2t is anyway, this is 0 because g theta 2 would be 0. So this would be same as just integral over all those t's such that g theta 1t is positive and psi t g theta 2t gt, which is same as integral over t g theta 1t is positive psi t g theta 2t upon g theta 1t into g theta 1t. Now I can divide it by g theta 1t. And in fact, here I can include this only where g theta 2 is positive also. Right? In fact, I can do this as g theta 1t is positive, g theta 2 is positive. Is that okay? So g theta 1t is positive, g theta 2 is positive. Now I break this into two parts, one t less than x0, one, maybe there is no need to write it down this for the time being. So this is okay. And now I write down this as one t less than x0, integral over all those t's such that g theta 1t is positive, t less than x0, psi t g theta 2t upon g theta 1t g theta 1t dt plus integral over all those t, whatever it is, psi t over here, sorry, t greater than or equal to x0. I'm just breaking this integral into further one t less than x0, one t greater than or equal to x0. What can you say about this? In this case, psi t is less than or equal to 0. And g theta 2t upon g theta 1t would be less than or equal to c. Right? So this would always be greater than or equal to c times psi t g theta 1t dt. This is greater than or equal to integral over same range. Let me not write it down. Because for t less than x0, psi t is less than or equal to 0. It is negative quantity. And g theta 2t upon g theta 1t for t less than x0 would be less than c. Because g theta 2 x0 upon g theta 1 x0 is c. This is less than or equal to c. When you multiply it by a negative quantity, then equality would be other way. So psi t times this would be greater than or equal to psi t times c. Is that okay? So this would be bigger than or equal to c times psi t g theta 1t dt. Yeah? You see, in this case, psi t is negative. G theta 2t upon g theta 1t is less than or equal to c. A quantity is less than or equal to c. If I multiply it by a negative quantity, what happens? Inequality changes. Psi was negative. So multiply it by that. So psi is the same That inequality has become greater than or equal to C. What happens over here? Psi is positive. What about g theta 2t upon g theta 1t for t greater than or equal to x naught? Greater than or equal to C. Psi is positive. So inequality doesn't change in this case. So it would also be C times integral over. And what is that? That is C times Is that okay? The second part is exactly the same. You have to just use the increasing part of. Right. Yeah, greater than or equal to C. Yes, that is greater than or equal to C because it is increasing. Yeah, so this is, this should be greater than or equal to C. You're right. Because g theta 2 x naught upon g theta 1 x naught is C, and it is increasing. So for t greater than or equal to x naught, g theta 2t upon g theta 1t should be bigger than or equal to C. Is that okay? So let me stop over here. Basically, the idea of this is very simple, that if you have MLR, and if there is a function psi which changes sign at most once, then expected value of psi t would also change signs at most once. And the sign change would be exactly the same way as that of psi. If psi changes sign from negative to positive, expected value of psi would also change sign from negative to positive. Is that okay? Means unless expected value psi t is positive throughout or it is negative throughout. If there is a change in sign, it would be in the same direction, from negative to positive. Psi is changing from negative to positive. Okay. So next time we'll derive the most powerful. This would be useful. This lemma, deriving this and generalize lemma Pearson lemma will give me the most powerful.